here we go. I'm going to jump into sharing my screen here and getting into, I start off with this slide here. This is a picture of Chichen Itza, and it's a pyramid in Mexico. And I start out with this slide because it's a great example of a structure that was made a long time ago and is exhibiting properties that would be very difficult, if not impossible, to replicate today. This picture was taken in the afternoon as the sun is setting on the equinox, and you'll notice that the edge of the pyramid is casting a shadow onto the staircase that makes it look like a snake. There's the, snake's body down there and the head at the bottom. And it's not like you could just say, okay, let's build this giant structure and we'll wait until the equinox comes, and then we'll call everybody out of the jungle to rotate it in place to make it do this. They had to know from the very beginning, from stone one, exactly how to build this to make it do this. This is showing you that these folks probably knew, first of all, that we lived on a sphere, that we were going around the sun, about the idea of equinoxes and solstices in the first place, probably about precession and a bunch of very, technical, mathematical, geometric information that you would need to be able to predict this phenomenon to be physically possible. And this was something that Nassim Haramein, an independent researcher who was trying to figure out the geometry of space-time, discovered on a vacation, really. He was just trying to get away from his normal patterning and went to Mexico, and it started him thinking, whoever built this knew some serious geometry, and maybe there's a clue as to the geometry of the structure of the inhabitant thing that we're inside of right now called space-time. And that is fundamental to unified field theory. In a very short synopsis of Nassim Haramein's unified field theory, he wanted to figure out why it is that we can measure space itself to be completely filled with energy. It used to be called the plenum. It used to be called the ether. This is before Einstein, right? And everything started to come back to the ether or the plenum, or what's now called the 0-point field, or the quantum foam, or the vacuum, or space, or God, or mana, or chi, or prana. It's had all these different names in all these different cultures. But at a certain point in the history of physics, when everything started to emerge from and go back to this mysterious property of space-time itself called the ether, it started to sound a little too magical for the scientists, which we can understand, right? Physicists don't want to be mystics. They don't want to be considered spiritual beings or gurus or, somebody that is speaking in metaphor. They want to collect actual data of actual observations of actual things, not just make up some stuff and give it a name and throw it into their theory. And so in order to get rid of this magical idea of prana or mana or the ether or the plenum, they said, well, yeah, we're measuring space to be completely filled with energy, but we can't just go around saying that it's infinitely full of energy, or else what are we saying, really? We have to give some finite numbers. And so they did something in physics called renormalization. And this is basically a fancy word for adding in a mathematical constant and renormalizing a number that would normally be infinite to make it finite. In other words, putting a cutoff value and a fudge factor, right? And as it turns out, this is an infinite fudge factor, because if you're cutting off a value that's infinite, it doesn't matter where you cut it off. You're cutting off a vast amount of information on there. And so basically they took a constant. It wasn't arbitrary, right? They used the cosmological constant and various other observations, and basically said, okay, we'll say that the energy in space itself is really, 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 really full, but it's not infinite. And they gave it a cutoff value. And this process is called renormalization. And Nassim Haramein looks at that and says, yeah, but by doing that, you are throwing off a lot. You're saying that something that's maybe infinite or nearly infinite is not infinite. And by doing that, they lost the ether. They lost the plenum. They lost the 0-point field. And the details around all this are rather complex and very ornate, and I don't have the time to go into all that physics, but I'll cut to the chase, which is if you make an error at the base of your model and then you try to build upon that to the very end, you might end up saying, okay, according to our calculations, there's a certain amount of mass in the universe. Let's go look for it. And when they looked for it in their telescopes, they said, uh-oh, we're missing some of the mass. And the answer is they're missing 95% of the mass, right? You've heard about this. They've been looking for this dark matter stuff that they can't find, and it represents 95% of the mass of the universe. Maybe if you have a theory that is only predicting 5% of what you can observe, there might have been an issue with the equations in that theory. And that's basically what Nassim Haramein is saying, that they shouldn't have renormalized the energy in the fabric of the vacuum. And when you do not renormalize it, then everything starts to make sense. Then you realize that inside the structure of space, it is so incredibly filled with energy that everything we observe actually emerges from and returns to this source field of energy, right? This is what David Wilcock calls the source field. It's the same thing, okay? And now we're finding evidence here in ancient cultures that these guys knew the geometry of the space, because if you want to figure out why it is that space is full, even though we consider it to be completely empty, you have to maybe come up with a theory of how that's even possible. It's got to be the biggest anomaly in the history of physics. We measure space to be completely filled, but I can move my hand right here. I don't feel anything. What do you mean? This isn't infinitely dense. I know I'm in the atmosphere and there's air here, and if a hurricane comes, it could knock over my house. But if I'm floating between galaxies and I move my hand like this, is there a viscosity to this? Is there anything there? As it turns out, there is. Casimir in 1940s or something came up with an experiment to measure the fabric of the vacuum density, the density of the quantum vacuum. And as it turns out, and we don't have time to go into the details of how they got to this, the vacuum is very, very, very full, nearly infinitely full with energy. And we perceive it as empty, perhaps because the structure of the space itself is in a perfectly balanced equilibrium state.